So the last couple of times we looked at a single charge moving through a magnetic field and the force being exerted on it. We then looked at a right hand rule to tell us the direction of the force that's being applied to it. Um, Working with one charge it can be useful in some cases. You just looking at how a mass spectrometer works, and that's really all there is to it. Is the fact that different isotopes have different masses will affect the radius of the circular path that uh, they'll move in a uniform magnetic field, since isotopes of the same element will have the same charge. Uh, Today, though, we're going to look at something that's going to lead us into a topic that's way more practical. And for us on the human scale, we can't really work with just one charge, but we can work with many, many charges moving through a current carrying wire. So the big goal today is to figure out uh, the force and the direction, uh, the magnetic force on a current carrying wire. So really, we're going to come back. We're going to look at force on a moving charge. Force is equal to Q, uh, the quantity of the charge times the velocity of that charge times the strength of the magnetic field times the sine of the angle relative to that magnetic field. Well, if I'm talking about a current carrying wire, if I want to know the velocity of the charges in that wire, really velocity is just distance over time, but if my wire has a set length, the velocity is going to be equal to the length of the wire over time. Now, this Q part, if it's a current carrying wire, um, you know, figure out how many charges there are each second, or really we just know that I current times time um, lets us know the amount of charge that flows through the wire in a certain amount of time. Um, so Q is equal to current times time. Well, if I now replace these things in here, I now have force is equal to, Q we've replaced with current times time. I'll even pop that in parentheses. Velocity we're replacing with length of the wire divided by time. B, we won't replace anything with, same thing with sine, sine of theta relative to the magnetic field. Okay. Thing here is I've got time here and time on the bottom here. Those times are canceled. So really the big equation we're going to be using today, magnetic force on a current carrying wire is equal to the current on the wire times the length of the wire times the magnetic field strength that that wire's in. Multiply that by the sine of the angle relative to the magnetic field. Okay. I like this equation mainly because of all the capital letters in it. I know that's a stupid reason to like an equation, but it looks way different than any other one we've used. Okay. And once again, force is still in newtons. All right. So really what we're saying is I'm even going to just jump right into the practice problem here. All right. So we've got a metal rod, 0.5 meters long with a mass of 0.05 kilograms. I can even, let's go through this. So my rod, and it looks like my rod is actually going to have we're going to try to run a current through it because we're going to put this rod perpendicular to a uniform magnetic field of 0.55 teslas, and that magnetic field is going to be coming, it's going away from us, so it's going into the screen. So we're going to indicate that, with circles with X's in it. And I'm going to do a lot of this magnetic field diagram here. All right, and let's even say that we've got our metal rod. You know what, that's fine. It doesn't have to be perfectly straight. All right, the rod here, 0.15 meters long. And it's going to have a mass of 0.05 kilograms. They want to know, I'll even do this stuff here, right? So length of the rod, 0.15 meters. Mass of the rod that they're giving us for some reason is 0.05 kilograms. Strength of the magnetic field they said was 0.55 Teslas, okay? And they want us to find A, the direction, and B, the magnitude of the electric current needed to levitate the rod. Okay, so once again, they've suspended the rod from two thin flexible wires, and they want to know essentially if I cut the wires, what strength of current will be enough to oppose the force of gravity? Because we know the force of gravity is going to pull down on this wire, and we need to set that. We need a magnetic force. That's hardly legible. We just need to know, how do I get the magnetic force to equal the force of gravity so that my rod, if I cut the wires, essentially just hovers there, it levitates, okay? So at this point, I'm looking at setting the force of gravity equal to the magnetic force, okay? So I can actually figure out F pretty quick, okay? Because the force of gravity is just equal to mass times acceleration due to gravity. I know I'm asking you to do something from like first quarter, so let's just do that real quick. So the mass we said was 0.05 kilograms, so not to convert anything there. Acceleration due to gravity is still 9.81 meters per second squared. I'll actually get out a calculator for that one. All right, so I've got 0.05 times 9.81. 0.49 is what I'm going to round that to. Okay, 0.49 newtons. Okay, that's the weight downward for that rod. Okay, so that means my force, my magnetic force, is going to have to be equal to, well, actually, we can even call that negative. It's equal to 0.49 newtons, okay? Because these things have to be equal to each other, just opposite signs. So I just snuck that negative there because downward. All right. So now I need to figure out the direction of this force. How am I going to figure out what direction this is going to go? So we kind of have a right-hand rule for this one as well. We're still going to use essentially the right-hand rule. And since we're talking about an electric current, we're talking about negative charges, okay? So I know that my magnetic field is going into the screen. It's going away from me. And this means I'm going to start off by putting my thumb in the direction of my electric current. Of magnetic force. I want it to go, so my thumb is going straight up. That is could be a really thick thumb. All right, so then, and I'm going to need to be able to, if that's the thumb on my right hand, I'm going to need to curl my fingers downward. Okay, so that means my fingers are actually going to be pointed this way. That's a better hand than last time. Okay, this way, if I set my hand this way, my magnetic force is going up. My fingers are now in a way so that I can curl them into the screen. Okay, this is my right hand. I'll even label that. So that way I know the palm's not facing me. The palm is facing the screen. Okay, so thumb's the direction of the force. My palm is facing the direction of the magnetic field. This means that my current has to be going to the right. Okay, it's kind of a new right-hand rule. Really, thumb, if you put your palm in the direction of the magnetic field, fingers in the direction of the current, stick your thumb out, that's the direction of force. So let's even go force, current, and then in this case, magnetic field's going in, palm faces it. It's just one way that you can actually use a right-hand rule to make this a little bit easier. Okay, so I can already answer A. So that means the answer to A is the current goes to the right. All right, A's done. Can scroll down here a little bit. All right, so now then you want to know B. What is the magnitude of the electric current? Okay, so we're looking for I. I think the easiest way to do this is to do some algebraic stuff. So if I've got force is equal to I, L, B, and in this case, they even said, the rod is perpendicular to the magnetic field. So I'm looking at the sine of 90, that's 1. I'm not even going to include it down here because I don't need to worry about the math. I need to get I by itself. So if I just divide both sides by length times strength of the magnetic field, I have I by itself. So current is equal to the magnetic force divided by the length of the wire times the strength of the magnetic field. I already know those numbers. I just need to plug them in. So the force we said was 0.49 newtons. And we're going to divide that by the length of the wire. In this case, it's a whole metal rod, 0.15 meters, times the strength of the magnetic field, which is 0.55 Teslas. That looks easy enough to just plug into a calculator. So I've got 0.49 divided by parentheses 0.15 times 0.55 close parentheses equals 5.9. Looks close enough to me. So that means the electric current is 5.9 amps. That's how much current we need to send through the rod from left to right in order to levitate or get that rod to hover within this magnetic field. That's actually a pretty strong magnetic field. But yeah, so that's really the force on a whole current carrying wire. And that's going to be really useful for what we move into next time, which is electric motors. So good luck with the practice problems.